This United States, sorry, that's the Donald Trump.
In example number 2, they give us 2 points. They say the point P is 23, comma 150. Oh, those are big numbers. And point Q is 45, comma 340. And they want us to find the average rate of change. And so basically we're going to say f of b minus f of a all over b minus a. And so this is a, this is f of a, this is b, this is f of b. Now what this is referring to is, this is actually an experimental biologist wanted to know the rates of population growth in a controlled laboratory of fruit flies. And so this was the actual growth where X was the time in days and P was the number of flies. Okay, so your textbook has it written as the number of flies P over delta T. Now you could see why you would want to know like the average rate of change of, in other words, how many fruit flies would there be over a certain period of time. So practically, from a practical perspective, on day 23 there were 150 fruit flies. Okay. On day 45 there were 340. So in a period of about 20 days, you little more than doubled the number of fruit flies.
Wow.
Right? So we want to break this down and get like a per day unit, the average rate of change. And so we're going to just plug the numbers in. We're going to say 340 minus 150 all over 45 minus 23. And remember, that's the average rate of change. Okay? And so that breaks down to about 190 over 22, which is about 8.6 fruit flies a day. Now, I suppose what I want to point out to you guys, though, is the graph. So I'm going to draw the graph. I'm just going to freehand sketch it. The graph looks like this. And so, well, I'll explain that. This is point P, and this is point Q. And so, if we were to think of this in terms of what it really is, we're just taking the average, the slope, between these 2 points.
Is this the thing where you can't plug in 0, but then you plug in 0?
Well, we're not, no, not quite. So this would be 23, this would be 45, and then this right here would be 150, and this right here would be 340. Now here's the thing. In the real world, the fruit flies at some point in time, they don't produce as much, usually because of conditions in the lab. For example, if there are too many fruit flies, there may not be enough resources, not enough food for every fruit fly that is born to live or sustain.
Oh, this is in the lab.
Yeah, this is in a lab, but this is what we call the logistic model. This is a very common model for biological or ecological surveys. And so what happens is the environment that you're in can only sustain a certain number of fruit flies.
So if it was like out in nature, would it be an exponential function?
Yes, but exponentially you wouldn't grow forever, right? So think of like bacteria. It doubles every day. Well, actually they double even quicker, but to make it simple, we'll say that I start off with 1 cell bacteria, and then that doubles into 2 cells, and then doubles and doubles and doubles and doubles and doubles. Well, if something doesn't get rid of the bacteria, the whole planet would be bacteria. So there's things that can get rid of the bacteria. But the point of this is that 8.6 fruit flies a day is just a snapshot or a portion, an average rate of change, but clearly the rate of change is different for down here because the slope is different here, and the slope is different here. So we can take a snapshot of a certain portion and take a look at it. In fact, the slope at this particular point is a little bit different than the slope of my average rate of change. Okay?